Oh my gosh.
for individual grades each. So every single one of us has a different score on this, right?
Exactly.
Okay, just checking.
This is actually, I put the class average into my test student. So these are the class average grades right now. And each of yours, you'll have your own grade related to your own performance. Yeah. All right. Anybody have any questions? I had a few questions. Oh, I have a chat. Good morning. Anybody have any questions from the midterm? Has everybody seen that? Looked at it? Looked at your midterm? It was graded. Okay. Overall, it was pretty well. Let me tell you something about it. Let me see. Where is this? All right. I got to get in the groove of how things work. It's been a little while. There we go. All right. Yeah, the average on the midterm was a 77, which is fine. Yeah.
Just Professor, I have a question about the average grade 0 homework turn in. I have a mistake, but I never put 0 homework, and I have a good amount, 87. That's why I always correct my homework and just submit it again. And this is count with the 0 homework.
What's happening? So that is what your average would be if you had turned in no homework.
Oh, okay.
Yep. So that's just a hypothetical, right? Just for the people, because I don't really calculate your true homework grade until the end of the semester, because I allow people to turn stuff in late. So I don't really know what your homework grade is until then. So I just give a range.
Okay.
So if you turned everything in and it's all good, then you're closer to the average with 100 homework, with all the homework. Yeah.
Okay.
Yeah. And if you've not turned in much, then you're closer to the average with no homework turned in. Yeah.
Okay.
It's pretty understand. So yeah, any number I give right now for the homework is not going to be truly accurate, because I haven't looked at the corrections yet, and people can turn stuff in late and all that kind of stuff. So I just give a range where it could be. Yeah.
Okay.
Anything else, guys? Okay. So the nice thing that we managed to do was we took the midterm right before the spring break, so we can basically kind of start fresh. There's nothing to review unless you have any leftover questions from stuff. We're going to jump into a new chapter. Yay. Right after we got so used to not having to show up for class for a week. All right, let me see. So if there's no other questions about anything, we're going to get right back into chapter 3. Everybody's good out there? Okay. You guys have a good break? Did anybody sneak out of the city?
Not much. I have a tooth infection.
I'm sorry. Oh man.
Yeah, I just put it all the time in the medicine and painkiller.
I'm sorry.
Yeah.
Man, that's rough.
Yes.
All right. I'm sorry. I went up to an area called Lake Forest. I did some hiking. I did a little too much hiking, I think. Knocked me out. And then I took some time at the beach. It was great. It was good. It was fun. That's the first trip I've taken, obviously, since the beginning of the situation we're in. But it was nice to get the hell out of here. I needed a change of scenery. So anyway, hopefully your break went okay. Hopefully you're all recharged. Okay. So let's get into chapter 3. If nobody, okay, all right. I'm sorry if it was a rough week for anybody. I always, whenever I ask that kind of question, how was your weekend or how was whatever, there's always a few people like, Oh, it was terrible. I'm like, oh shit, I'm sorry. Okay. So what we're getting into now, we are getting into graphing stuff. So you can, some of these terms hopefully are familiar. The intercepts of a line, right? We're talking about rate of change. So the rate of change of something. Does somebody know what we're going to call that eventually related to lines? What would the rate of change be related to with respect to lines? Does anyone know? The rate of change of a linear function. Does anyone know?
That's the slope.
There it is. Yeah. So right now we're just going to call it rate of change. And eventually we're going to identify it as the slope of a line. Anyway, okay. Blah, 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 blah. So let's look. So of course they have to do something about Back to the Future. When you get to 88 miles an hour, watch out. If you've never seen Back to the Future, I'm not sure what to do with you. You need to see Back to the Future. You just have to. You might hate it. That's fine. You should see it. Please. So let's see. So when we say miles per hour, a lot of us don't stop and realize that's an actual ratio. So a lot of people see MPH as a single unit, right? So I don't know if anybody here also has done that before, where you think of MPH as just a single unit, but it's miles per hour. So it is actually a ratio. So that is what we call a rate of change. For every hour, my position changes by 88 miles. Okay, I like it. All right. So if you make $100 a day for doing a certain job, how much money would you make in a 5-day work week? Now, I guess we're assuming no taxes. I guess this is under the table. I don't know. This is an easy one. Jump in on this while it's still easy questions.
500.
Yeah, it's crazy. So $100 a day. If you work for 5 days, that's obviously $500. Now, if you want to look at it a different way, $100 per day. So if I work for 5 days, bam, bam, that's $500. Just multiply across, right? But again, you don't have to do that. It's pretty simple. I don't need the grid. It's a very simple problem. I don't need the grid to help me out. So would you say that this rate and this rate are equivalent rates?
Yes.
Yes. What's the easiest way to see that they're equivalent numerically?
That they go into so the 100 goes into the 500 equally.
Well, look right here. What can I do with this fraction?
You can reduce it.
Yeah, just reduce it. So it reduces to $100 a day. So these are equivalent rates. I like it. Now, the assumption I'm making is that the guy doesn't say on Monday, okay, I'll pay $100 a day. And then on Wednesday, they say, I'm going to start paying you $90 a day now. So we're assuming that the rate stays the same in case anybody in their brain is thinking, I don't know, Jeff. So obviously the rate has to stay the same, right? So we're assuming that's true. So that's okay. Maybe, maybe, maybe. All right, let me clear this. Nothing amazing yet. Some very boring shit, maybe. I don't know how you feel about this. That's a nice way to ease back into this. All right, now we're going to get a little more interesting here. This first one, number 3, is not that bad. Take a second and do that. What number 3 says. And let me make a real quick plea. Nobody has to do this, but if you are able to turn your camera on right now, I would love it. I'm so happy that I can see Trisha. So if Trisha did not have her camera on, I would feel mental anguish.
Sorry, I'm eating breakfast. Sorry.
Oh, you're fine. Like I said, if you don't want to turn your camera on because you're eating breakfast or whatever, or you haven't taking a shower or whatever. But if you can, that's appreciated. All right. So who's got this bad boy? How do you do that? 60 miles for 4 hours would be how many miles for 2 hours?
30 or
Yeah.
120, right? Or
No, careful. So I'm going down. So how do I
okay.
go 4 to 2? I divide by 2. So I got to do the same thing to the top. All right, let me stop and really make sure everybody's with me. Once I've got a ratio set up, the only way to maintain equivalence, oh shit, the only way to make it stay the same numerically is to do the same thing to the bottom and the top. I got to either divide both of them by something or multiply both of them by something. So what about this? The unit rate is if the bottom is 1. The word unit, in fact, a little quick sidebar. I've been watching too much of the George Floyd trial. Sorry, a little quick side note. Can somebody remind me what a prime number is? Versus,
A number that can only be divided by itself.
yeah, like 17 is prime because the only way to break up 17 is 1 times 17. Now, somebody else tell me, do you know what the word composite means? For what kind of number is a composite number?
Isn't it just every other number that's not prime? Am I crazy? Is that wrong?
No, it's right, Tristan, but I did ask for somebody else, but that's all right. So this would be something like 9, because 9 is 3 times 3 and 1 times 9. So composite number, like Tristan said, is all the things that aren't prime. Now you gotta be careful. The number 1 is given a special name. The number 1 is called the unit number. So that the whole reason I want to do this side note is just so you know that the word unit, I know it has a different meaning when you talk about that dog is a unit, raw, but in math, the word unit just means 1. And I don't know if anybody's ever heard of the unit circle. Has anyone ever heard of the unit circle? What the hell would that be? Well, that's a circle with a radius of 1. Right. And of course, this looks like a sad Pac-Man, but that's all right. So to make this into a unit rate, I want to make it something per 1. So how the hell would I do that? How do I make that into something per 1 hour instead of per 4 hours? What would I do?
We have to divide it
Divided by
to
4.
4.
Yeah. So what's 60 divided by 4?
15.
15. So there'll be 15 miles an hour. So if I'm traveling at 60 miles for 4 hours, that means I was traveling at 15 miles per hour. Okay. Now this is where things get really neat. So I'm not going to say a word. And you guys don't say anything either. It's a little bit of a challenge. They give you a hint. Can you make this have, instead of a 4, I want this to have a 10 in the bottom. Don't say anything. To give you a hint, you could do this. Let me give you another hint. If I wanted you to take this guy and make the bottom become 10, isn't it easier to do that if I rewrite it like this first? How would I make this bottom become 10? I would just multiply by.
It's gonna be 32 on 24 minutes, or 2.4 per hour.
What is happening? All right, wait a minute. Listen. It wants to have 10 in the denominator. I'm not asking for a unit rate, which I'm not sure if that's what you were doing. I need to have 10 in the bottom. So how do I make this become something with a 2 in the bottom?
Divided by 2.
Divided by 2.
Yeah. So if I divide by 2, I get $160 every 2 days. Now, how do I make that become something over 10 days? What do I do to the top and bottom?
And times it by 5.
That's 5.
All right, get in there. So that becomes 10 days and 5 times 160. All right, thanks for all the help, everybody. All right. So $800 for 10 days.
We can just divide, multiply by 2.5 at the beginning without.
You totally could. You totally could. Yeah, because that's how you make 4 become 10, but that's not necessarily everybody could see that easily. You could also divide this by 4 and make it per 1, right? But if I have a 4, that's 80 per 1. And then if I multiply by 10, I still get 800 per 10. All right. All right. Let me stop for a minute. Hopefully, well, anyway, I have no idea. Maybe some of you guys are bored. But I don't think you've played with fractions in exactly this way before necessarily. This idea of reducing it and then building it back up, right? We've done both of those, but we haven't really quite, I don't think many of us have done something quite like this. Reduce it and then build it back up specifically to make it easier to make the bottom become something else. Okay. But all this means is if somebody said they would pay me $320 for 4 days and the job became 10 days long, stay with me now. If somebody said, I'll pay you $320 for 4 days of work, and then no fault of our own, the job becomes 10 days long, what are we going to argue to be paid? $800, correct? That would be the only fair payment they could make. Maybe even some extra for whatever, but still, to make it completely fair to both sides, they better pay me $800. Okay, maybe. All right. Let me clear all this away. So what is a rate of change? It's a ratio showing how one variable changes as another variable changes, right? So as days change, the amount of money made changes. Rate of change. And normally the bottom is like a time, but it doesn't have to be. So let me clear all this away. Every example they give us so far is a distance per time or a money per time. All right, and that's what we normally think of as a rate of changes per time. Now look at number 6. All right, little challenge for you guys. Take a minute and figure out, don't say anything yet, which person is going faster. Whoa, I got a lot of chats. I'm sorry, I'm not paying any attention. I got a lot of answers from earlier. I'm sorry, Trisha. All right, so if somebody's got me an answer for this, let me see. Anybody willing to answer this that hasn't spoken yet? Anybody out there got the answer for this that hasn't said anything to me yet? Is there anybody else out there besides the people that are talking to me? Does anyone have an answer?
40 miles in 3 hours is faster.
All right, let's see. So I got a vote for 40 and 3. How did you figure that out, Ethan?
I just divided 3 from 40.
Oh, okay. So you got a unit rate. What'd you get for that?
Let me check again. I think it was 13.3.
Yeah. Right. I like it. And then you converted this to a unit rate also?
Yes, sir. It's 12.5.
Yeah, there you go. So I like that. So that's what I meant by scaling up or down. So you decided to scale down and just divided those real quick in the old calculator. I like it. So obviously then this person is going faster. And why is it easier to compare these two? Because right now this is based on a different amount of time. So I can't really compare them as they're given to me. In fact, I would hazard a guess that most of us, when we looked at these two, you couldn't just tell immediately who was going faster. I would think most of us. Okay, maybe. Same for me. When I first looked at that, I'm like, I don't know. And then you have to think about it and then you get there. Anybody else do this a different way? Everybody did it that way? I don't blame you. That's the standard way to make it like a unit rate. I like it. I could also, let me give you a different way to do this. I could actually also take these, multiply this by 4, and multiply this by 3. And this goes 160 and 12, and this goes 150 and 12. So this still, it's another way to show me that is still faster. Okay, maybe. Boring, I know. Boring, Jeff, but still, maybe not totally boring. I don't know. Oh, shit. All right, let me clear all this away. Here we go. It's going away. Bye, stuff. Bam. Whoa. Oh, boy. This book is so jumpy. Let's see this one. All right. So there's going to be a few questions possibly that give you rates in different ways. Can you fill this sentence in? This shouldn't be too bad. Number 7, this person's jogging at a certain rate. For every how many minutes the runner jogs, how many meters?
2 minutes, 400 meters.
Craziness, right? That shouldn't be too bad. But again, it's always a little weird when they give us the same information in different formats. Oh, okay. Somebody's telling me that it was neat. It wasn't so boring. Okay, I appreciate that. I don't think it's boring. I love this shit, but you know me, I'm weird. So now I want you to realize something. Every 2 minutes, they jog 400 meters, and we're going to assume that they can maintain this pace for a long time. So this person is not me. All right. This is a different person. So is there a quick way? Well, just take a minute and fill in. Can you fill in this chart? Don't say anything. Try to fill that chart in, only knowing this. Good Lord, Jeff. Why do you have to, like a football coach trying to diagram a play? Stop it. So every 2 minutes, the runner jogs another 400 meters. So who's got what goes here?
800.
800.
Yeah, every 2 minutes, they're going to add 400 meters to their distance. So then if I just kept going, this would be 6.
6.
This would be,
1200.
Well,
yeah. Does anybody see a different way to look at this? Look at 2 and 400, 4 and 800, 6 and 1200. What do I do to 2 to make it become 400? What do I do to 4 to make it become 800? Do you guys see a different way to do this? Anybody? Is that a weird question? It's probably a weird question. Maybe I shouldn't have asked that yet.
Was it like doubled?
Well, doubled, and then you throw a couple zeros on, right? So it's times 200.
100.
So what's 8 times 200?
1600.
1600. Doesn't that still maintain the plus 400?
Yes.
Isn't that neat? Isn't that just like I'm talking about like a grain of sand level of, okay, that's interesting, right? There's a additive way to do this and there's a multiplicative way to do this, because, and it kind of makes sense because addition does lead to multiplication. Anyway, I don't know if you guys, so I can either add 400 or I can multiply by 200 and I get to 2000 either way. And I could do it again, add another 400 or multiply by 200, same answer. Okay, so you guys know what this is leading to. Well, what's the unit rate on this thing? 400 meters for, holy crap, Jeff, 400 meters for 2 minutes. The unit rate, of course, would be 200 meters per minute. So that's why it makes sense. I could just take the number of minutes and multiply by 200. That's another way I could do this. Okay, that's enough, Jeff. Now you're making it boring. I'm sorry. All right. This is all very important. This is the connection we're going to have to make later to really understand what slope is. In your future. Okay. All right. Let me clear this. Some of you guys who remember stuff like, anybody remember y equals mx plus b? I don't know.
I kind of do, but I don't want to.
I understand. It's in that part of your brain that you've locked away of horrible experiences. I'm sorry if that's true.
Very far into my brain.
I'm sorry. I'm going to try to gently coax it out over the course of a couple sections here. But this is a precursor to understanding that equation. All right, I'm not going to do too much with that yet. I was going to go off on something, but I'm going to leave that for later. So let me clear all this away. Bam. All right. Oh, shit. I hate when they do this. All right. So we need to know the 2 minutes, 400 meters. Okay. Yeah, this is kind of silly. This obviously is what kind of growth. Do you guys remember there were two main kinds of growth we discussed? There was exponential growth, and there was also what kind of growth? There was exponential growth.
And linear growth?
And linear growth. I love it. So this is really obviously linear growth because I keep adding the same amount each step. So that's what they mean by number 9. We already did number 10. We already did number 11. So let me just write down number 11 so we remember what the hell we just did. Oh man, there's more chats. I can't keep it. Okay. Oh shit. All right. I forgot how to use everything. So as a unit rate, what was it? 400 meters in 2 minutes, right? So then we made that 200 meters per minute. Wow. I tell you something. My writing has only gotten worse. Let me try. Let's see what we can do here, Jeff. There we go. Okay. That's what that says. Meters per, ooh, all right. So do number 12. Do number 12. Oh, look how excited I am about this silly problem. Do number 12. Notice they tell you how much to round. It's always exciting to see that. That means you can use your calculator. Your calculator. So let's see who remembers how the hell to do this. I want to go from minutes to seconds, right? Right now I've got it meters per minute. I want meters per second. So where am I going to put minutes?
On the top.
On the top. And on the bottom I got seconds. So 60 seconds and 1 minute. Die. So it's 200 divided by 6.
3.33.
Yeah. 3.33 meters per second. It's always interesting to take your speed and convert it to per second. You feel like you're just flying. Now, look at number 13. This is kind of interesting they did that. What we just did is we converted this to a rate per second. But what would I use to answer number 13? Would I use this?
The rate per minute.
Yeah, hell yeah. So take a minute and do number 13. You know the rate up here per minute. So how far will this person go in 40 minutes? So figure that out. And again, please, dear God, if we're doing anything that doesn't make sense, you have to let me know, right? Don't just sit there and go, everybody else seems to understand. Don't assume that. It's not necessarily true. In fact, several of you might not even be listening to me right now. I don't know. You love and you went away. Okay. So who's got that? We got 40 minutes.
Would it be 8,000 meters in 40 minutes?
Yeah. So I got 200 meters per minute. Die, multiply. And of course, didn't we already determine this? The way we did the table earlier, I said you could multiply the minutes by 200. That's exactly what we're doing. That's exactly what just happened. It's so nice to see. We already kind of knew this, and that's what the grid leads to. Now, of course, if I want to do number 14, what should I use?
The rate per second.
Yeah, rate per second. So then I can get, now let me show you. You could actually do this the other way around. Die. So whatever the hell 40 times 3.33 is. 53. No, Jeff. 120, 13, 133 point something. I don't know.
133.2.
All right. And that'll be meters, right? Because that's the unit that's left alive. Okay. So rates of change can also be seen as conversions, right? It's a conversion between meters and seconds or between minutes and meters. It's conversions. So we can use them in grids. Okay, maybe. I love you guys. All right, let me clear all this away. Clear? Okay. All right. Can you write a formula? Oh, all right. So this is too bad. I should have. Oh man, there's so many chats. I can't do chats. Okay. Based on the previous two questions. All right. Can you write a formula for finding the distance traveled by an object when you know the speed and amount of time traveling at the speed? Oh, okay. So like, what did we do up here? To figure out the distance, we took 200 times 40, correct? The 200 represented what?
The meters.
Meters per
minute.
So the 200 represented a speed, which will officially designate as the rate of change of position. Oh God, Jeff. Oh shit. Stay with me now. Why'd you say all those words, Jeff? I don't know. So this is what we consider to be speed. It's the rate of change of position. You guys with me? So that's why we'll use the letter R for that. And what was the 40? The 40, of course, was the time. So incredibly enough, I'm going to use the letter T for that, right? Because I'm a boring math teacher. So the distance an object travels equals the rate at which it's traveling times
The
time it travels for, right? Which we all know that stupid equation. We all know. We use it all the time, but do we consider it to be a formula? No. Right? If you're going 80 miles an hour for a couple hours, you know how far that you're going to go, right? You don't need a formula for that. But this is officially the formula for distance. And the nice thing about it is, if you look at it, it's the word dirt, right? D equals RT, dirt. Okay, D equals RT. That's a huge formula. I'm almost certain that most of you guys have heard of that formula before, maybe.
Nope.
No? Okay. Well, now you know it. You've used it and you just didn't know you were using it, right? Okay. So let me clear this away. Actually, let me show you something on the side here. There's a more general formula. The amount equals the rate times time. Let me tell you this. What if I typed 80 words per minute, right? And I typed for 5 minutes. How many words would I type? 80 words a minute, and I type for 5 minutes. How many words would I type? Sorry?
400.
Yeah. So the amount that I do is equal to the rate of change times the time over which I do the thing. So that'll be 400 words. Right? So this is the more general formula. I just put an A there for amount. But when we're talking about amount of distance traveled, we use D for distance instead. That's where the D equals RT comes from. Okay, maybe. And again, this is a very simple formula. It captures a very simple idea that we all do without realizing there's a formula that captures it, right? So formulas aren't necessary to do things. They're just capturing what we do. That's what a formula does. All right, so let me clear this away. So what I'm trying to say is you don't need to know the formula before you can do something with it. The formula is just our way of writing down, oh, here's what we do. Here's the thing we do. Oh, okay. All right, let me clear this away. Oh, blah, blah, blah. Who cares? All right. Oh, okay. All right. Now here's where things get a little bit more interesting. Cab ride in Las Vegas. Where was I? I took a cab ride in Italy somewhere. I can't remember. And I thought for sure I was going to die. I was pretty certain we were going to die. So if you ever go to Italy, I don't know, maybe don't take a cab. Anyway, sorry. It's an interesting roller coaster. So read through this real quick. So we're in Las Vegas. Sorry. So now we're starting to bring together a lot of different things we've been working on, right? We're bringing together scatter plot, plotting points. We're bringing together stuff we just talked about, this linear growth. All right, so take a minute and finish the table. There's not really a good shortcut we could use on this one. This one's not as easy as the earlier one. And if you're curious, I'll tell you why that's true. But what's the most useful number they give you here that will help you fill in this chart? How much? Go ahead, sorry.
Mile.
260 per mile. So you can see that. How do you see that in the chart already? How's that number showing up in the chart already?
So your initial cost is going to be 510, and then if you add 260, it becomes 770 for the first mile.
I like it. Now, everybody finish the chart, plot the points. I'll sit here and I'll just sit here. Maybe I'll drink. All right, guys. Let's go quicker. I don't know if you have a calculator near you. Maybe some of you guys don't need it. What's this next entry here?
1290.
Well, 90, I love it. You just add 260. Jeff, you could do it. Here you go, buddy. And then if you add another 260,
1550.
Yeah.
I like it. And then, of course,
1810.
1810. I like it. That sounds more like a history test, but that's all right. So you should already know before you plot the points, the pattern the points will make. We know that this is what kind of growth?
Linear growth.
Linear growth, because we keep adding to find the next output. So I know that this is going to make a line when I draw the points, right? I already know that ahead of time. So let's see, the scale they gave us isn't the easiest to graph these points on, but you do the best you can. So 7 is right in the middle. 770 is really close to 8. And then 1030, let's see, 1030. So the 10 is just going to be right above the 30, right above the 10. You can do it, Jeff. I don't know how to words anymore. 3 is 1290. So it's going to be right in the middle is 13. Everybody with me? 13 is right in the middle. So it's going to be right underneath that, which I really can't do. So I'm just going to put it in the middle. 1550 at 4. 15 is right in the middle. So it's going to be a little bit above. It's going to be in the middle of the middle of the thing in the middle. Okay. And then for 5, it's 1810. Thank God it's just a little bit above 18. And sure enough, that does look like a straight line, right? In fact, let me show off something. You can do it, Jeff. Do. Sorry. Let's see if I can do that. Look at that. Jeff didn't do too bad. He did kind of bad, but relatively close. Oh well, too bad, Jeff. If I make this dot bigger. All right. All right. Anyway, it didn't tell you to connect the dots, I don't think, right? Use that observation about a pattern to connect the points. You just did number 2, Jeff. Good job. Okay, but that should be something you guys like. If I just put points, I'm like, let me connect the points, please. And obviously it's a straight line, like we said. Okay. So this is one thing students really hate after word problems. I think that's the number one thing students hate. The next thing they hate is graphing. And what's really sad about that is graphing a relationship is creating a visual out of a situation, and a lot of people can appreciate visuals. So math likes to take a situation and create a visual out of it so that we can kind of interpret what the hell's going on and what to expect and so forth, right? Anyway, so we haven't gotten too crazy of a graph stuff yet. We're dealing with straight lines here. Let me clear all this away. Clear. Now, some interesting stuff. Dadgummit, Jeff. You guys should still have your graph. Here are those intercepts that I previewed were coming up earlier. The Y-intercept, incredibly enough, is where the graph crosses the Y-axis. It's where it intercepts the Y-axis. So what was the Y-intercept for our line up here? Where does it hit the Y? What's the Y-axis? Which axis is the Y-axis? Distance or cost?
The
Cost.
Cost, yeah. The Y-axis is the one normally that's going vertically. And of course, the X-axis is here. So what was the Y-intercept? Where did it hit? You should have yours. Let me redraw mine real quick. Here's 510 and 770 and so forth, blah, blah, blah. So there's the line again. So what was the Y-intercept? Where's the point where it hits the Y-axis?
Would that be the 0, 5, 10?
Yeah, Yeah, so it hits the y-axis right there. That's the y-intercept. This is the y-axis. So the y-intercept is 0, 5, 10. What do you think is going to be true about any y-intercept? What must be true if I have a line and it hits the y-axis? You can have any place where it hits the y-axis, but what's always going to be true when it hits the y-axis? What's going to be true about the x piece of the point? Is the x piece 1? Is the x piece -1? What's going to be true about the x piece always?
The 0 is always going to be there.
Yeah, so like this is the point 0, 2, and this is the point 0, -1. Why is the 0 got to be in front? Because if it wasn't a 0, that means I would have moved away from the y-axis. So I really want this to make all the sense in the world. Every y-intercept, the first number has to be freaking 0 so that I'm not moving left or right, because then I won't be on the y-axis. That only makes sense. I only want to move up and down. I don't want to move left and right. So what's always true for the y-intercept? X equals 0. Look how big of a point I'm making out of this. It must mean something. Would this graph have an x-intercept?
Yes,
If you did what?
if it was 0, 0.
Well, no. Okay. Theoretically, this graph has an x-intercept, which is kind of weird, but that would mean I'd have to go back. I'd have to have negative distance. Is that going to happen? No, I really want you guys okay with this. There's no x-intercept for this graph. There isn't. Because I can't have negative distance, correct? That's weird. What does that mean? It's not even you get in the cab and it starts driving backwards, because that would still just be distance, not negative distance. It would have to mean that you get in the cab and you get sucked into a wormhole or something, right? It doesn't make any sense. I really want you guys to be okay with this. There is no x-intercept because the only place it could hit the x-axis is in a region that I can't even get to. Okay, I don't know if that freaks anybody out. Maybe the fact that I said something about a wormhole freaks you out. I'm sorry. So it's okay. There are graphs that don't have an x-intercept. Some graphs don't have a y-intercept. No big deal. All right. Let me clear all this away. I love you guys. You're all like, oh, this is so much better than spring break, Jeff. All right, let me clear all this away. All right, so this is kind of boring stuff. Blah, 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 blah. Who cares? All right, so here's where we finally get to slope. So let me kind of build my way up to this. I need to put a handout up on the what do you call it? Let me do this. Let me get off my ass for a second. Let's do this. Let me turn Mars off. Mars. I knew Mars is fake. It's all CGI. Shut up. Let me see. All right. Thankfully, the house is not too bad. So, my house is crooked. All right. Now, some of this should be familiar to a lot of us, but again, maybe it's been a while for some of us. Hold on, let me try to focus a little bit. All right. So if I have a linear relationship, let's see. All right, this is always the exciting part. All right, so if I have a linear relationship, let's say it goes like this. Oh, my scale sucks so bad. That's too bad, Jeff. The scale really does suck a bad amount of stuff. Oh, well, you'll be all right, dude. All right, let's see if I can do this. Do. All right, not too terrible. Now, what I want us to do, let's say that this is distance in miles. Let's say this is miles. Yeah, and this is hours. I don't know. So we're not moving too fast, but I don't care. Now, can we figure out? No, this is a bad. It doesn't matter, Jeff. You'll be fine. Can we figure out how fast this thing is moving using just what I have here, just these points? So what I'm trying to say is this. After 1 hour, I'm at the 0 mile mark, right? So maybe there's a track, there's a 0 mile mark, and there's a -1 mile mark, and there's a 1 mile mark. So I'm moving along, I'm at the -2 mile mark, and then I'm at the 0 mile mark. I'm 0 miles, right? And then I'm at the 2 mile mark. So let me ask you this. So to go from here to here, how many miles does that represent? From this point to that point, how much did the miles change? What position am I at? I'm at the
1 mile.
No.
Mile.
Somebody help me out. What's this point? What's this point? What point is this?
1 0.
1.
1 0.
0 1. Yeah.
0 1 would be there. That's 1 0. The first number is always left and right. So it's right 1. Second number is always up and down. I didn't go up and down at all. So 1 0. Is everybody with me? That would be 0 1. What point is this?
Two.
Yeah, you can't go wrong with that one. All right, 2 2. Now, let's go another step. Everybody stay with me. What the shit does this mean in plain English? I'm at the what mile mark after how many hours?
1 mile.
No. Mm-mm.
Or you're at the 0 mile mark after
I'm
1.
at the 0 mile mark after 1 hour. What does this mean? I'm at the, can't go wrong here, 2 mile mark after 2 hours. All right, let me stop for a minute. Stay with me, everybody. So what is my rate of change of position? What is my speed that I'm traveling at? Well, how many miles did I go? How many miles did I go?
2.
Yeah, I went 2 miles in how many hours?
1.
I heard
One.
Yeah,
1 hour.
1.
1 hour, correct?
1.
1 hour, 2 miles. And so there's my speed, 2 miles per hour. Now, why do I should not need to do this? Is there a quicker visual way to see my speed? To get from here to there, my miles changed by 2, right? Is everybody with me? My miles changed by 2, and my time changed by 1. Right? When I go up or down, that's how much this changes. When I go left or right, that's how much this changes. So my miles changed by 2 as my time changed by 1. Which is really what we did here, isn't it? 2 minus 0. Well, 2 minus 0 is 2. That's that distance. And 2 minus 1 is 1. That's how we got the 1 there. I'm sorry, here. So there are 2 ways to get slope. one way is to count. In fact, does anybody remember what slope is in English? Well, what should I call this? What am I doing visually from this point to here? I'm going up, which means I am what? What will a
Rising.
balloon
Rising,
rising? So slope is rise
overrun.
over run. Does that sound familiar to anybody?
It does to me.
Okay. Rise over run. Yes, somebody else got it in the chat too. So if I have a visualization of the problem, if I have a graph of the problem, I could always step out the slope. Does that make sense what I just said? Oh shit. Lot points have always confused me. I'm not sure what to do with that. Let's do another example. And then I'll bring the algebraic way to look at this in a minute. Let's do another example. Let me draw a better picture. All right, hold on. I'm going to erase all this. You ready? Let's just keep this nice here. Let's see. Let's do, yeah. All right. Well, all right. We'll do. Sure. It's the same thing, Joe. All right. Let's do this. All right. So we'll have one going like this. We'll make this big, we'll make this big, make this big. All right, so 1, 2, 3, 4, 1, 2, 3, 4, -1, -2, -3, -1, -2, -4, blah, blah, blah. Okay, so now we got this line, pretend like that's a straight line. All right, let's identify the points real quick. What's this point here?
-3, -2.
No.
No, opposite, -2, -3.
Yeah, first one's always got to be X direction, left and right. The second one's always got to be Y direction, up and down.
Oh.
I like that sound. So what's this guy here? How much did I move left or right to get to this point?
-1, 0,
Negative.
-1.
0.
And then I didn't go up or down at all.
Mhm.
What would we call this point? What's this point? Why is it special? It's the what?
X-axis. Or no, the x-intercept.
There you go, x-intercept. It's the point that intersects with the x-axis. So we call it the x-intercept. And of course, that would be the y-intercept. And what is this point?
0, 3.
Good. Didn't move left or right at all. Only went up 3. All right. Now take any 2 points, right? Take any 2 points. How much do I, from this point to that point? How do I get there? And one thing I want you guys to realize is, has anyone ever been to Utah? This is a strange question, I know. All right, Utah freaks me out because it's so perfectly, I'm talking about Salt Lake City. The roads are just so freaking perfectly a grid. It's even too much for Mr. Math here, right? I'm like, this is too much. Because I grew up in Virginia and their roads, we have roads that intersect themselves, you know, so it's like spaghetti. It's interesting. Anyway, you've been to Utah, not been to Utah. It's nice. There's really good hiking, but it also felt very strange. A friend of mine is Mormon and I am not religious. So I kept thinking they're going to point at me and go, oh, you are not. They were fine. They were nice. So I can only drive north, south, and I can only drive east, west, right? So how do I get to that point from this point? How much do I drive? How much do I
3.
drive up? 3. So I rise over run, that's our slope.
Mhm.
I rise 3.
Run
I
1.
have to run
1.
what? So the slope here is 3. Which means every step I take, my output grows 3 times that. Every step I take, my output is 3 times that. Every step I take, my output is 3 times that. Which kind of goes back to that problem where we multiplied by 200 instead of adding whatever it was. Do you guys remember that? So here I could kind of, there's a multiplication by 3 in this somewhere. Okay, now. Well, okay, so let's talk about the algebra behind this. Does it matter what points I pick? In fact, let's do this. Oh, I'm so excited. From this point to this point, how far do I have to go up?
6.
6. And then how much do I have to run
2.
over?
2.
1, 2.
Mhm.
Which still reduces to 3 to 1. So of course it's the same slope. So does it matter for a straight line? Does it matter what 2 points I pick to figure out the slope? Should it matter what 2 points I pick? I really want you guys, if it did matter, that would mean it could be a straight line. It would have to curve. If it wasn't going up and over the same amount every single time, it would not be a straight line then. Does that make sense? If it wasn't going up as much as while it's going over the same amount each time, it's not a straight line. So let me ask this again. Does it matter what 2 points I pick to figure out the slope of a straight line?
No.
No, it does not matter because it has to maintain the same growth rate, right? It has to be a linear growth. It's got to be the same amount each time. And even if I pick 2 points that are further apart, they will reduce back down to the same thing. If it didn't, it means it curves somewhere. It starts to go up faster or starts to go up slower, right? Then you have parabolas and you have who knows what else, other weird shit, right? Hyperbolas and you got ellipses and you have who knows. Okay, maybe. Right now we're just dealing with straight lines. Now, what does that have to do with anything, Jeff? I don't know. What's another way? I could just look at the points and tell. I really want this to make all the sense in the world. How do we know this is 3? Because that's 3 and that's 0, right? That's their y pieces. So how much did the y change by? 3. How about from here to here? Do you guys see? How much did the y change from here to there? From this point to that point? How much did the y change? You could do it. How much did the y change? It was -3 here and now it's 0. So how much did the y change?
By 3.
It increased by 3. And then how much does the y change from this point to that point?
Increased by 3.
Holy shnikes. I gotta be careful. I hear a small one somewhere out there. Gotta watch my language. All right, stay with me. So how do I figure out the rise? If I'm just given 2 points, let me call them x1, y1, and x2, y2. How do I figure out the rise? It'll be the difference in the y's. That rhymes. Do you understand how that's nice? Rise over run is y's over the other guys. So how do I know this changed by, how do I know the top is 3? Because this changed by 3. What's 3 minus 0? 3. And what about the run? Well, the run is how much the x's change. So it's going to be x2 minus x1. So what is 0 minus -1? What is 0 minus -1? could do it. So the top is 3 minus 0. And the bottom would be 0 minus -1. What is 0 minus -1? What do the two negatives do?
Positive.
Positive.
So don't you still get 3 over 1?
Yes.
All right. All right. So this looks very important. This contains slope is the visual. If I have a graph to work with, I can just count how much it rises or falls. And then here is the algebraic part. All right. Let me see if I can push this a little bit more. Let me do one more thing. I know I've got a lot of shit happening up here, but oh well. If I go from this point to that point, let's do this. How much does it change here? Does it rise? No, it falls, right? So this slope would be, it goes down 3, correct? It went down 3, back 1. Doesn't it go back?
Yes.
And what's -3 divided by -1?
3.
Still freaking 3. Everything's 3. Of course, everything's 3 because this is a line. It's going to have the same slope. No matter if you go forward or backward, it's going to be 3. Isn't that kind of crazy? At the same time, it's not crazy. It's a freaking line. It's got to always have 3 is the slope. Maybe. All right, now I'm going to erase all this. And I think this is the last thing we'll do. Not for our whole lives, but I mean, just for today. All right, here we go. You ready? I'm going to erase. Here it goes. All right. Wait, what is the? Oh, okay. What is the x2 and x1? Oh, okay, good. I got you. All right. Any general point is x, y. You with me? Any general point is x comma y. Is everybody cool with that? All right. How do I identify a specific point? Well, one way I could do it is to say, I have one point, I'll call it x1, y1, and I have another point, I'll call it x2, y2. This just means the first point's y and the first point's x, the second point's y, and the second point's x. So this point 0, let's say -1, 0, and this could be the point 0, 3. So that's the first point's x, the first point's y, the second point's x, the second point's y. The little subscript in mathematics just means a specific variable value, right? This means any point. It could be that point, it could be that point, it could be that point, it could be the point up there. This means any point. These mean 2 specific points. Okay, I like it. Very good, very good, very good. All right, let me erase all this. Here we go. So let me put this formula back up here. I see the red, okay. Yeah, the red's a little washed out. Sorry. Really done. Oh well. All right, so if I just give you 2 points, find the slope between those 2 points. So how the shit do I do this? Well, until you get comfortable, you pick one. Let me call this one x1, y1. Is that cool? That's the first point. So I'm going to call it x1, y1. So I'm going to call this x2, y2. That's crazy sauce. So now I'm just going to plug all that stuff into my equation. y2 is 7 minus y1. Here's where people get really confused. there's a minus in the equation, and what is y1? -5. So y2 minus y1 over x2 minus x1. So it's how much the y's change divided by how much the x's change. So what do I get here?
Our slope is gonna be 6.
Say again, sorry, what?
Our slope is gonna be 6.
No,
Oh, sorry.
step by step.
12
So this
Two.
becomes positive
plus
12.
12.
What's -2 minus 4?
-6.
There you go.
2 is gonna be -2.
Yes, -2. I like it. And real quick, so 4, -5. I'm not going to do this perfectly, but just let me do this real quick. 4, -5, -2, 7. Good Lord, Jeff. -2, 7. It's not a perfect graph, but you can see one big thing is it's a negative slope, right? How do I know this is a negative slope? Because the line is going down. Crazy sauce, right? I don't know. That's my phrase of the day. The line is going down. That's why it makes sense that it came out negative. And as it goes down 2, it moves over 1. Goes down 2, it moves over 1. Goes down 2, it moves over 1. Blah, 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 blah. So that's why it makes sense. It's -2. All right. That was a little bit quick, but we're basically out of time. All right. So I'll tell you what, next time I'll find my slope handout so I can give you guys something to work on together. And if you really hate slope and lines, oh well, it's too bad, we're in it. We're gonna start to do it. If you have any old questions that have never made sense, now will be the time to bring them up about slope and lines and stuff. So we'll do more of this tomorrow. Okay, otherwise, we're done for today. Let me know if you need to hang out afterwards.
Thank you, sir.
You're welcome.
Have a good day.
You too.
Thank you, Professor. See you later.
I'm full of math. I have plenty to give. Everybody else all right?
Yeah, I'm just copying the whiteboard now.
Oh yeah, good.
All right, bye, Professor.
See you.
Thank you.
All right, I'm gonna head out.